We will start with number 30. Believe it was that one with the 8K and the 6K, and we are supposed to find the shear moment diagrams. And then, of course, the next step would be to locate the maximum. Then the next step would be bending stress. So, is this the one you did? Is this the right one? Yeah. All right, good. I'm gonna sit. So I did the moment about A to find BY. Just kind of worked ahead a little bit here to save some time. I got 30.25K at BY and 13.75 at AY. Which makes sense. BY is going to carry more load because it overhangs. AY will carry less load, even though the 8K is bigger. BY is just a lot more loaded. All right. So once we have that, we can go for the shear diagram. That's the V equals 0 line. And we'll just follow the forces. I'm going to go up because it points up. You kind of just figure out your own scale as you're doing it. The more you do, you'll kind of get a feel for it. You don't want your scale too big, or it just gets to be a giant graph on your paper. 13.75K. Then it comes down, and it comes down 1.5K for every foot. So in 8 feet, 8 times 1.5, it's going to come down a total of 12 in this 8 feet. There's nothing else going on in there, so you can just calculate how much it comes down and bring it down. So it comes down to near like 2. So again, just keep your scale right. Looks like, whoops, that's the wrong thing to do. Times minus 175. Everyone get that? Because it's a uniform distribution, it's a straight line slope. Okay, it's not a curve because this is not changing, right? It's uniform, so that makes this a straight line. Then we see the 8K. So it drops a total of 8 to 6.25. Okay. These are all forces, shear force. Then for 8 feet until it sees BY, we continue at that same slope. So down to here, whoops. So again, it's going to drop that 8 times 1.5, which is like 12, down to 18.25. Then it sees BY, goes way back up, goes up a total of 32.5, and that's up to 12. So it's actually below the 13. It's right in here. If I was to keep my scale correct. Then it goes over 4 at 1.5 drop. So it drops 6, kind of halfway. And then the last thing is this last 6. So again, if you complete it back to 0, you know you've got it. Okay. So it has plus region, has negative region, goes back to plus region. And clearly the maximum V is 18.25K. And that's the number we'll use to calculate shear stress when we do that next step. So the maximum value that shows up on the graph. Good? Questions? Okay. All right. Keep going to the moment diagram. Moment diagram you can develop from the shear diagram, starting with our m equals 0. We know there's maximum or minimums here where it crosses 0. So there'll be a max up here and probably a min down here because the slope is positive to begin with, right? So it's positive. And it's bigger than it is here. It's less at this point, like that. So if I'm not sure, I kind of draw these little slope marks in to give me a feel for it. It is a slope here, a straight line slope. So this is going to be parabolic. So the progression is horizontal gives me a straight line slope. A straight line slope gives me parabolic, second degree parabola. If there was another one, it would be third degree parabola, right? So this comes up. It doesn't get to flat because it's here. So it's supposed to have some slope up still. And then it goes to quite a bit of slope down. So that should not be like a tangent. There should be a little point in there, technically. So then it goes quite a bit negative, like pretty slopey negative down here. So this is going to come over and drop down. So there's a point there, and there's going to be a point here. And then it's going to go positive slope to less positive slope. So something like that. Again, your scale can be different. It can be much more less dramatic, like it could look like this, right? And then kind of like this, and then like this. How you draw that, like the kind of the scale of the graph doesn't matter, right? What matters is that we locate this point and this point. And since this seems kind of like a dramatic drop, I'm guessing this is probably our max, but we should calculate both. So for this one, it's going to be this area. So to get the moment, you look at the shear and you look left. And you have to use it all, everything to the left. So this one's going to be, and the way I do it is this rectangle would be the 175 times the 8 feet. So that's the rectangle. And then I need the triangle, which is going to be 1/2 the base times the height, and the height is this here. So it's the 1375 minus the 175, so that's 12. So you have to do those two areas and just be sure when you do the triangle not to use the whole height, right? Because part of that height got used up in the rectangle. I get 62 for this one. And that is a moment because it's feet times kips. So that's good. We know that this area is 62. To get the moment here, we need both areas. This area, and then take that area away because it's positive, this is negative. So we have this area that we have to figure out. Again, I do a rectangle and a triangle. So I'll call this moment min, and then I'll calculate this area here, which is 625 times its length of 8 feet. So that's the rectangle. Plus 1/2 the base, 8 times the height, and the height's going to be the difference between those two. So the 1825 minus the 625 is it 12 again? I think so. Yeah, it is. So that's this big negative area. And I can call it a negative area, and then I gotta add this area, because when you do the moment here, you gotta look entirely left. So that means I gotta add this 62. So the negative area here and the positive area here, and that'll give me the moment here. I get 36. So it's not bigger, it's actually smaller. So 36 down here for the min, 62 up here for the max. So my graph is like, should be shifted, you know, so it looked right. So really, the graph really like is up here and then down here smaller and then here. This being 36, that being the 62. It's good. Yeah, and again, this is what we need, right? To take it to FB equals MC over I. That's our moment. If we knew what the beam was, we can get C and I, and we can come up with the bending stress. They didn't give us the beam. All right. This one, the next one. 33. Make sure I transferred it over correctly. 14 and 10 coming down, a distribution of 3 kips per foot for 12 feet and 8 feet at the end. This is called a simply supported beam because the supports are at the ends. This is not a simple supported beam because the supports are not at the end. So I did not do the moment on this one yet. So I'd start with doing a moment about A to get BY. It's going to be 14 times 3, and that's negative 10 times 6. It's negative, that's this one. Then I need the 3 kip per foot times its full length of 12 feet times its half length for the moment arm of 6 feet. So this is often missed or forgotten about. We got to concentrate this, and then we got to multiply it times its lever arm. That's all of them, and BY times 20. That's positive. Does anybody have a number for BY?
15.9 kips.
Anybody else have 15.9? Alice does. So that's I give you for A1.
44.1 kips.
It's like we have a total of 24 coming down. 3 times 12 is 36. 60, yeah, it looks like it adds up. So just some clues. This one had a deflection curve that looked like this. So deflection is how it is going to move around, right? So you can see that the concavity of the deflection is up, and then the concavity of this deflection over here is down. That's how we end up with this positive and negative moment thing. The deflection curve goes in like an S shape. This one, the deflection curve would just be like this, all concave up, right? If it deflected, that means the moment's going to be entirely positive. So that's a clue. But once you start to pick up this deflection thing, it tells you like, oh, this moment is all positive. Where this one tells me, oh, this moment is both positive and negative. So that's helpful. All right, the graph. Shear diagram. Follow these. It's like it goes quite a bit up. 44.1 K. Then it comes down 3 kips per foot, so it's going to come down 36. So that's pretty steep, right? 3 times, oh, sorry, it's going to come down 9. 3 times 3. Not that steep then. Comes down 9. $35.1. Then it goes down 14. And 21.1. Then it goes down another 9, 3 times 3. To 12.1. Gonna run out of space. I'll make it work though. Hasn't crossed yet. Then it goes down. So what's this? 6. This is 6 out here. 6 times 3 is 18. So there it crossed. Oh, I got to get the 10 down, don't I? Dang, I'm running out of space. This is 2.1. Yeah, I'm going to need a better graph probably, but that's all right. We'll keep going. So down the 10, we got the 14 drop, the 10 drop to 2.1, and then 6 times 3 is 18. So then it finally crosses out to here. $15.9. Then what happens out here?
Straight line to the
Yeah, nothing. And if we've done it right, our 15.9 should return. It does. So yeah, kind of a jerky graph, but that's because of the concentrated loads. Vmax is 44.1, often right near a support. That's where the shear is going to be greatest. Here's our 0 mark. Not really sure where that is, but we can figure it out. But I can draw the graph. Positive and less positive and less positive. Then it goes negative. So positive means it's going to come out here steep and get less steep. And it's a curve. Then it's going to be also a curve, but just less curvy. So hard to draw, but there's a point there. There's a point there. It's still curvy. Then it goes, stays positive just for a second, this little bit right here, and then it goes to 0 right there. Then it goes negative, barely negative. So this is a nice transition tangent curve to here. And then from here, it's a straight line. So that's straight. And the rest of these are all parabolic curves. Second degree parabola. Again, drawing it, you just do your best to draw it and note the points. You don't have to find those values, not completely necessary. What we need is this maximum value right there. That's M max. What's up, Todd? Are you just learning something?
I'll talk to it. I can see what I'm on.
Okay, no problem. All right, so to find M max this is new. How do we do this? Anyone figure it out?
I did.
Similar triangles?
I don't know what I did on.
You don't remember what you did?
Well, for the like the squares and the triangles, I just did the normal part for that small little gap.
Yeah,
I did 3 cubes per foot divided by 2.1 kip
okay,
to get the distance, and then I just did a triangle with that.
yep. That's the way to do it. I'm gonna draw this section right here a little bigger and put the horizontal in like right here. So this is a blow up of this region right here, where I know this is 2.1 from there to there, right? And this is 15.9 from there to there. That everyone see what I've done? Just blown up that crossing. This is the spot we want. So the way to do this is what's called similar triangles, because this slope can build a triangle from here to here. And we know this height, it's 15.1, 15.9 plus 2.1. That's what that height is. And we know this length. This length is the 6 foot. So if you can build 2 triangles where you know both legs of one of the triangles and you don't know one leg of the other triangle and they share the hypotenuse, that's similar triangles. And you can just build ratios. So for this one, it is 6 feet, the big triangle, to this, which is 15.9, 17.9, and then that is, looks like it's 18 kips. So the big triangle is 6 feet to 18. So my scale's way off, but that's all right. And then the small triangle is X. And so these 2 legs need to be both on top over 2.1. So you can set up that ratio for similar triangles and come up with the X value, which you need to get the moment. Because we need to know the area all over here, including this little positive area right there, that little positive area. Because this is all negative area, this is positive. So that gives me an X of, and you just do the algebra there, once you set up those 2 ratios. 2.1 times, it's pretty small, it's 0.7, this little distance. So then to get M max, we have to do all of these areas, right? To get the moment. So the other way to do it is just go up and section the beam. I really don't know which way is easier. They're both, you know, a little bit time consuming. I'd probably just do the areas because I can do a rectangle here, a triangle here, a rectangle, triangle, and then this little small triangle to get that moment. So it's a fair bit of work. Like you gotta be careful and make sure you get your numbers right. So I'll try to do it. I'll do the 35.1. Put the units in because that's important. Okay. Times this distance, which is 3 feet. So that's this big rectangle here. Kind of color code some of it. That's that rectangle. And then I got to add to it 1/2 the base of 3 feet times the height, which is this. So it's the 44 minus the 35. Yeah, probably. I'm afraid to do it in my head. It's definitely not. So now we got that triangle accounted for. Now I'm going to do this rectangle here, which is the 12.1, the 2.1, sorry. Oh, the 2.1 is the lowest. It is the 12.1. Yeah, bigger diagram would have helped. Times 3 feet. So that's that. Then I need another triangle, 1/2 the base, 3 feet times this height. So it's the 21.1 minus the 12.1. Which is 9 again. So now I have that triangle. And all I need is this little one right here. This little leftover triangle, which is 1/2. The base is my x, 0.7 feet. And the height is 2.1. And that should be the moment max. I've got all my areas accounted for. Everybody get a max moment?
Mine's different, but I didn't get 0.7 fast.
Oh, you didn't get the 0.7?
I got like 1.48.
Do you see how I got it?
Yeah.
So it's called similar triangles.
Yeah.
You build the ratios. So this big triangle we know. Yeah, so that's 6. And then the height is the 2.1 plus the 15.9. Yeah, 18. So that builds the ratio for the triangle you know. And then this is the small triangle that we don't know x.
Yeah.
And that's x to 2.1, x to 2.1. You got to put the legs both on top. So this and this got to be on top. And then the other verticals got to be down below. You can't mix those. So that's called similar triangles. The ratios have to be true to each other because it's a straight line. If it was a curve, you couldn't do this, but it's a straight line. So then you just algebraically solve it, do that division, multiply this across, and you get 0.7. That was the trickiest part, like to locate this 0. Gets really tricky if that's a parabolic curve. It's like, oh boy. All right, let's see if we can crunch this. First time through, I get 169. Oh, tip feet. I'll do it again.
I get that too.
Yeah, that's a good sign. It's a long process when you have, a lot going on a beam. That'd be the number we'd use in bending stress, so. Questions? Takes some practice, doing it a few times. All right, let's turn those in. Let's do a extra credit one, because you all are here. And you all need rewarded for that. So this will be an aluminum bar. And I'm gonna make that cross section to look like 1 inch by 4 inches. 1 inch by 4 inches. We're going to support it at the ends. Be a simple one. We'll put a distribution on it. We're gonna span it 6 feet. We'll make the distribution 30 pounds per foot. And then we're also going to put a concentrated load on it of 500 pounds. And that'll be 2 feet over. So this is 4 feet here. Absolutely. Here, I'll give you a whole pad. He's like one left or two on there. Is there one? Yeah. That's funny. Yeah, and just write extra credit on it, make sure your name's on it. And what we're gonna do is see if this thing is good or not, all the way out to bending stress. Okay? And to check it, I'm gonna model it in SolidWorks and run a load analysis on it. So as soon as you get it drawn, then I'll go to SolidWorks and draw it up. I haven't done this in a long time, so just check numbers, right? See how well SolidWorks is coming up with the stress on this thing. Most of you've had SolidWorks, right? Yeah. Alex, have you had SolidWorks? Yeah. So the distribution is 30 pounds per foot, 500 concentrated, 2 foot from the right end. We got AY and BY. 500 pound, yeah, we could be overstressing this, so good. I want it to be close. So process is you gotta find the reactions, then you gotta draw your diagrams, get that maximum moment, and then put it in MC over I. That's the plan. Everybody got it? Yeah, that's PSN. How are we doing? What do we get for AY and BY?
BY got 423.33. AY 256.67.
Oh, 6.7. 6.7. All right. Anybody else confirm this? Yeah,
Yeah.
okay. Great. Then we're gonna head into the shear diagram. Draw 4 times 30. 120. Something wrong. 136.67.
Right, 133.
Yeah. 6.7. Or 136.7.
Should be 256 minus 4 times 3, which is 120, right?
Yeah.
Yeah. 256.67 and a 120 minus. It's all good, Aiden. It's your calculator. Then we drop a total of 500, which is 363.
Yep.
Then we drop another 60. But what better be 423.33?
I guess I just put a 3 instead of a 6. I haven't done that. Mine came back.
I often, like I said, we're all on the spectrum. We're all dyslexic to some point. Like I can transfer numbers out of the book onto the problem and like mix up the loads, right? Just switch them. I think I got it. So yeah, you just really got to be careful. All right, very good. Gives us a decent moment diagram, not too crazy. At least we know right where that max is, right? It's gonna go up. It's gonna be curved, but I'm gonna draw it kind of full. Oh, sorry. Thanks. It's gonna be positive slope, but I'm gonna keep it kind of shallow. And then it gets less positive to here, so it's even shallower. To there. And then it's pretty negative, like it's gonna drop right off. And we have 1 max, so that's nice. We could tell that from the deflection curve. All concave up is going to be all positive in the moment. Then to get that M max, we need these areas, so it's the 136.67 times 6 feet. Plus the triangle.
So you only have to do the area math to the left of the max.
Correct, just to the left. 1/2 the base. Oh, wait, this is 4 feet, sorry. That was almost a mistake. Because the base here is 4 feet. One half the base times the height, which is the difference between those two. Which looks like 100.
120.
Oh yeah, 120. That should give it to us. $786. Foot-pounds. Anybody else get that?
Just mean in a one beam, we can have only one maximum moment, right?
On this one.
But in real, we can have two.
Well, this one. This first one we did. So this beam. Because it changes concavity and the deflection, it definitely had 2 maxes. Yep. But not every beam will. If it's,
Or 3.33, right? It's a, we get positive number instead of negative, right?
here,
For
The end
443,
on B.
yeah.
yeah. Going up,
Why it's down? It's going up.
yeah.
I'm just putting on top, you know.
Ah, you put it above. Yeah, so we follow the forces from the spot that we're at. So we were down here, so we went up. Right? The 423 to get back to 0. Yeah. All right, so far so good. Now we know our moment, we can go to the bending stress equation, which is MC over I. We can put in our moment, 786.68 foot-pounds. We need our C value, and so remember that C is from the neutral axis to the outermost fiber, and this thing was 4 inches tall by 1 inch. Right? So C is going to be what? 2 inches over I. So inertia for a rectangle is in the back of the book. So we just look up that formula for a rectangle. I think it's base height cubed over 12, but I'll check it. So inertia, base height cubed over 12 for the X, for a rectangle.
4 times 1 cubed over 12.
Yeah, so base is 1. 4 is the height, and that's what gets cubed over 12. So this is going to give us inches to the 4th down below. So we really need inches squared above. So we got to get rid of this foot. So we need 12 inches per foot to cross that. So once you get your units all to work out, your inertia is going to be inches to the 4th. We need inches squared above. That'll give us pounds per square inch, which is what we want. I get 3540.
Yeah. Yes, I know.
Yeah, but Because we switched that feet to inches, we got PSI, which is what we want. That's what the table's gonna give you is PSI or KSI.
And if we wanted to put pounds per foot, we would have to change the bottom.
Yeah, you'd have to get that to
Would the
feet.
12 change to 1?
No, this you probably wouldn't do. If you wanted it in pounds per foot squared, you'd have to get this unit, inches to the fourth. You'd have to do a factor of 12 to the 4 over 1 to the 4. But you're never gonna wanna do that, because the tables are always gonna give you PSI or KSI. The numbers get big, then you just take 1,000 away to get KSI. So aluminum, what is that material? For a yield. Looks like 35 KSI, 35,000. 35,000. So we're good. Let's see what SolidWorks came up with. So this is what you get. You get this dramatic thing. Huh?
That's what it would look like.
It always very dramatic on the deflection. Always dramatic. But that is the deflection curve. I fixed both ends. So really both ends would get to rotate, right? So I just fixed both ends. Maybe I don't think I can fix. Anyway, what do we get for stresses? So it really doesn't show any red, like maybe slightly reddish there. It's always hard to read this thing, right? You can get this in tabular form, but I don't know, that's not deep dark red. So it looks like, I mean, we came up with 3,000. They're coming up with what?
I can't see it.
It's 2.142 e to the 3. So they're coming up with like 21,000 for the reddish. The greenish is, I'm pretty sure that's right. Feel like it's a factor. Oh, it's using, yeah, so it's using 39,000. 3.9 for the yield, which is pretty close to what we had 35 in the book. So it's using a higher value.
You also can add factor of safety in it.
Oh, from the book?
Factor of safety, you can add factor of safety.
Yeah, you can add factor safety. Yep. Yep.
Oh, so it's saying the yield from the book, we're using a different number.
It's using a different number. It's using 39. The book uses 35, I think. Yeah. So it's not bad. It's close. Like our number is what, 3.5?
Yeah.
Yeah.
Now question why we learned this.
Why are we doing this? So we understand this. For sure. So we understand this. Yeah, so then we can get displacement. So this is the displacement graph. It's in millimeters. We can change that to inches. What you'll find, Alex, is most of the time we'll calc it by hand, and then we'll also use the software to check it. So that's just repetition. And if it's a critical part, that's important. Let's see if I want to change this, my fixed.
What's more trusted, the math or the simulator?
I would say if you really want confidence, if you want confidence to go up in your design, you want those to match. You want two different systems to match at least. And it'd be great if two different systems from two different people match. Then your confidence goes way up. If something's dramatically different, then
But if your math says it's not good, the
Yeah.
software says it's good.
yeah, I wouldn't.
Trust your math.
Yeah, I would do more work.
But
Yeah.
it should be more precise than we.
Yeah, absolutely. Let's see if can I fix I just want to fix an edge. Oh, let's do that. Because it's going to change the stresses if you allow it to rotate.
Oh, I get what you're saying. So like it would,
Yeah, right now it's fixing that whole end.
so,
It's not allowing end rotation.
gotcha.
So a pin and a roller allows end rotation. That's going to take a lot of stresses away. So let's do it this way. See if we can. Oh, substantially different.
Yeah.
Yeah, look at, now we're down,
Only blue.
yeah, exactly. So based on this upper yield, it's all down in here. See where it's at?
Yeah.
Yeah.
Everything's good.
And it's, we got 3.5 and look at, it's dialing in at very close to 3.5.
Oh, okay, cool.
So. Yeah, it's super fun to have both.
Yeah,
But like you said, I did this like in 2 minutes and we did this in like 15 minutes.
but it's like little things like that, like fixing the edge versus fixing.
Exactly, that's where your confidence will go up and down. Like when I first ran it, I thought like, oh, that's not what we have, is this fixed face. We have free end rotation, so. You'd want to, like, if it was a cantilever, that end is fixed, it's welded or whatever, that's when you want to fix that face.
Right.
So, yeah. All right, nice job, everybody. You have some more homework,
What's this called? Strength what?
huh?
What's this called?
The class,
No. It's just.
bending stress,
practice. Oh.
extra credit, man.
Extra credit.
Oh my God, I was losing it. Extra credit. So your homework is 3 and 12 out of chapter 14. So the only difference between 13 and 14 is you take it all the way to bending stress, right? 13 was just shear and moment diagrams. So now we're into 14 and it's 3 and 12. Oh, that was a good simulation. Especially if we would get the yield the same at 35.
Yeah.
Or we run our numbers. I bet that graph is spot on.
When drawing a free body, how would you? How would the edge versus the face like that, like alter the map?
You would draw, those would be two fixed ends.
Top and bottom?
Yeah,
Okay.
yeah. Well, end and end, right end and left end, right? So if you had two fixed ends, you would have to draw it like this. And then the free body diagram would be X, Y, and moment.
Oh. Okay.
Yeah, X. So this is what we call statically indeterminate. The reason is 1, 2, 3, 4, 5, 6 unknowns. Your 3 equations are not going to solve for that.
So how would you
So-
solve that?
Software.
Okay.
Yeah. Or multivariable problem, which I probably wouldn't even go there. Yeah, absolutely, Alex.